Right now, Voyager 1 is hurtling through interstellar space at 61,000 kilometers per hour. Sounds incredibly fast, doesn't it? But here's the thing. At that speed, it would take Voyager 70,000 years to reach the nearest star. 70,000 years. Nearly a quarter of modern human history. Today, we're diving into one simple but profound question. With our current technology, how fast can we actually travel through space? Not theory, not future dreams, but right now. And trust me, the answer will completely change how you see humanity's place among the stars. I'm curious, where are you listening from? Is your room bathed in soft afternoon light or wrapped in the quiet darkness of evening? If this resonates with you and you're curious to explore more mysteries together, feel free to stay a while longer. Maybe hit subscribe, drop a comment with your thoughts, or leave a quiet like to let me know you're here. Now let's begin. When we talk about traveling through space, we first need to understand something fundamental. Distance in space makes everything on Earth look like a speck of dust. The Moon, our nearest celestial neighbor, sits about 384,000 kilometers away. That might not sound like much in cosmic terms, but let me put it in perspective. If you could drive your car at highway speed, say 100 kilometers per hour, it would take you 160 days of non-stop driving to reach the Moon. No bathroom breaks, no sleep, just 4 months of constant driving through the vacuum of space. The Apollo missions of the late 1960s and early 1970s did something remarkable. They took 3 days to cover that distance, traveling at roughly 40,000 kilometers per hour during their translunar coast. That's faster than any commercial jet, faster than any bullet, faster than most things humans had ever built. For the first time in history, people were moving through space at speeds that seemed to defy imagination. But here's where it gets truly interesting. The fastest speed any human has ever traveled wasn't on the way to the Moon. It was on the way back. In May 1969, just 2 months before the first moon landing, 3 astronauts, Tom Stafford, John Young, and Eugene Cernan, were screaming back toward Earth aboard Apollo 10. They had just completed a full dress rehearsal for the moon landing, flying to within 15 kilometers of the lunar surface. As their capsule fell back into Earth's gravity well, it accelerated to an astonishing 39,897 kilometers per hour. That's 11 kilometers every single second. Think about that for a moment. In the time it takes you to say, 1 Mississippi, these 3 men had traveled 11 kilometers. They covered the length of Manhattan Island in about 2 seconds. They crossed the distance of a marathon in 3.8 seconds. This speed record has stood for over 55 years. No human has moved faster since. Not the space shuttle astronauts, not the International Space Station crew, not anyone. For a brief moment in 1969, 3 men became the fastest humans in history, moving at a velocity that still hasn't been matched. But here's the sobering reality. Even at this incredible speed, the fastest any human has ever traveled, it would still take 115,000 years to reach Proxima Centauri, our nearest neighboring star. Let that sink in. The fastest we've ever gone, and we'd need 115,000 years to reach the closest star. That's longer than modern humans have existed on Earth. That's longer than all of recorded human civilization, by a factor of 10. To make interstellar travel practical, say to reach Proxima Centauri in a single human lifetime of 80 years, we would need to travel roughly 4,000 times faster than Apollo 10's record speed. We're not talking about incremental improvements here. We're talking about a speed increase so massive, it requires fundamentally different physics. The Apollo program used chemical rockets, essentially controlled explosions that heated gas and expelled it at high velocity. These rockets operated close to their theoretical maximum efficiency. The laws of chemistry place hard limits on how fast you can throw atoms out the back of an engine, and Apollo was already approaching those limits. When the Saturn V rocket ignited its 5 F1 engines, it burned through fuel at an astonishing rate, about 15 tons per second. That's roughly the weight of 9 cars worth of fuel every single second, and 90% of the rocket's total weight at liftoff was fuel. Just 10% was rocket structure and payload. This incredible fuel-to-payload ratio is what enabled Apollo to reach the moon, but it also revealed the fundamental challenge: every bit of speed requires fuel, and that fuel itself requires more fuel to lift it. The Apollo astronauts were riding a controlled explosion, powerful enough to shake buildings 5 kilometers away from the launch pad, and yet, in cosmic terms, they were barely crawling. They reached the moon in 3 days, but the stars remained impossibly, incomprehensibly far away. Here's what makes this even more humbling. The Apollo capsules had no way to speed up during the journey. Once their engines shut down after the translunar injection burn, they were coasting. They moved at 40,000 kilometers per hour, not because they were accelerating, but because they had escaped Earth's gravity and were falling toward the moon. In space, once you're moving, you keep moving, but you're also not getting any faster unless you fire your engines again. And this is where the tyranny of the rocket equation becomes clear. The Apollo spacecraft couldn't carry enough fuel for continuous acceleration. The fuel required would have been so massive that no rocket could have lifted it. So they did what was possible: one big burn to escape Earth, a coast phase lasting 3 days, and then small correction burns. Efficient, elegant, and painfully limited. Yet despite these limitations, Apollo achieved something profound. It proved that humans could leave Earth's cradle, cross the cosmic ocean to another world, and return home. For 3 years, between 1968 and 1972, we sent 24 people to the moon. 12 of them walked on another world. We moved faster than any humans had ever moved before. But the stars remained out of reach. So, what's the fastest object we've ever built? The answer is yes. Dramatically, spectacularly yes. And to achieve it, we had to do something that seems counterintuitive. We aimed not outward into deep space, but inward, toward the sun. In August 2018, NASA launched the Parker Solar Probe with a mission that sounds almost suicidal: fly closer to the sun than any spacecraft in history, passing through the sun's outer atmosphere, the corona, where temperatures exceed 1 million degrees Celsius. But this isn't a story about temperature. It's a story about speed. Because to accomplish this mission, Parker had to become the fastest object humanity has ever built. As I speak, the Parker Solar Probe is conducting a cosmic dance around our star using the gravity of Venus to tighten its orbit with each pass. Every time it swings by Venus, it gets a gravitational kick that sends it screaming even closer to the sun. And as it approaches perihelion, the closest point in its orbit, it accelerates to a velocity that defies comprehension. At its peak, Parker reaches speeds of 692,000 kilometers per hour. That's 163 kilometers every single second. That's fast enough to travel from New York to Tokyo in less than a minute. Fast enough to circle the entire Earth in just 4 minutes. Fast enough to make the Apollo record look glacial. By comparison, Parker is traveling 17 times faster than those Apollo astronauts. To put this in perspective, if Parker flew over a football field, it would cross from one end zone to the other in less than 0.02 of a second, faster than a single frame of video. At its peak speed, Parker covers the distance from Earth to the Moon, that 3-day journey for Apollo, in just 33 minutes. This is the fastest speed any human-made object has ever achieved. Nothing we have built has moved faster. Parker holds the absolute record, and it's not even close. The second fastest spacecraft are moving at roughly half this velocity. But here's the thing, and I need you to understand this fully, even at 692,000 kilometers per hour, even at this mind-bending, record-shattering velocity that is 17 times faster than the fastest humans have ever traveled, it would still take Parker's solar probe 6 out of 300 years to reach Proxima Centauri. Let me say that again, 6,300 years. At our absolute fastest, that's longer than all of recorded human history. The Parker solar probe would have had to launch before humans invented writing, before the pyramids were built, before agriculture spread across the continents, and it would only now, in 2025, be reaching our nearest stellar neighbor. Think about what humanity was doing 6,300 years ago. We were just beginning to develop the first cities in Mesopotamia. The wheel had recently been invented. Bronze tools were cutting-edge technology, and if some ancient civilization had somehow launched a spacecraft at Parker's speed, back then it would be arriving at Proxima Centauri today. So, why is Parker so much faster than Apollo? The answer lies in orbital mechanics and energy. The Parker solar probe isn't fighting against the sun's gravity. It's falling toward it. And when you fall toward the sun from the outer solar system, you pick up speed at an extraordinary rate. The sun's gravity well is immensely deep, and Parker is diving into it, converting gravitational potential energy into kinetic energy with every kilometer it descends. The spacecraft achieves this through a carefully choreographed series of Venus flybys. Each encounter with Venus slows Parker down just enough to lower its perihelion, the closest point to the sun. And as that perihelion drops, Parker falls faster and faster toward the sun. It's like rolling a ball down a hill that gets steeper with every meter. By the time Parker reaches its closest approach, just 1 million kilometers from the sun's surface, well within the orbit of Mercury, it's moving at that astonishing 692,000 kilometers per hour. But this speed comes with a price. At perihelion, Parker spends just a few hours at peak velocity before climbing back out of the sun's gravity well. As it climbs, it slows down dramatically, trading speed for altitude. At aphelion, its farthest point from the sun, Parker is moving at a relatively sedate 39,000 kilometers per hour, slower even than Apollo. And here's what makes this both beautiful and frustrating. Parker's speed is orbital speed. It's not going anywhere in the long term. It's locked in an elliptical orbit around the sun, diving close and then retreating over and over. The spacecraft isn't journeying to the stars. It's studying our own star from an unprecedented vantage point. Its record-breaking speed is a consequence of its scientific mission, not an interstellar voyage. To actually use that speed for interstellar travel, we would need to escape the sun's gravity entirely, and that would require an enormous amount of additional energy. Parker can achieve 692,000 kilometers per hour while falling toward the sun, but to carry that speed out into interstellar space would require accelerating against the sun's pull the entire way out. The energy required would be staggering. The spacecraft itself is a marvel of engineering. To survive the intense solar radiation at perihelion, where the heat flux is roughly 500 times more intense than Earth orbit, Parker carries a heat shield made of carbon composite foam about 11 centimeters thick. Behind this shield, the instruments remain at room temperature, while the shield's sun-facing side endures temperatures of 370 degrees Celsius. But speed has another cost: navigation. At 163 kilometers per second, Parker is moving so fast that even light takes a noticeable time to communicate with Earth. Commands sent from mission control take time to reach the spacecraft, and by the time they arrive, Parker has already moved thousands of kilometers from where it was when the command was sent. The spacecraft must be largely autonomous during its close solar approaches, executing pre-programmed maneuvers without waiting for human input. So, here we are, with our speed champion, 692,000 kilometers per hour, the fastest human-made object ever created, fast enough to cross the solar system, fast enough to study the sun up close, fast enough to break every speed record in the history of space exploration. Yet still, not even close to fast enough for the stars, not by a factor of hundreds. The gulf between our fastest speed and the speed needed for practical interstellar travel remains vast, seemingly insurmountable, humbling in its immensity. But this raises an obvious question: why is space so impossibly vast? To truly understand why space travel is so challenging, we need to grasp something that our brains didn't evolve: to comprehend the sheer staggering scale of cosmic distances. Let me paint you a picture using a scale model that might help. Imagine shrinking the Earth down to the size of a marble, about 1 centimeter in diameter, small enough to hold between your thumb and forefinger. At this scale, the moon would be a pea about 3 millimeters across, sitting roughly 30 centimeters away, about the length of a ruler. The Apollo astronauts traveled the equivalent of a foot in this model. That 3-day journey was the distance from your hand to your elbow, close enough to reach out and touch. Now, let's go further. Mars, at its closest approach, would be a slightly smaller marble, about 9 meters away, across a large room. The distance Apollo covered in 3 days, Mars requires 7 months at similar speeds. We've gone from reaching distance to across the house distance. The sun would be a beach ball about 120 meters away, the length of a football field. Pluto, which New Horizons took 9.5 years to reach, would be a grain of sand about 5 kilometers distant, a comfortable bike ride. But here's where it gets truly humbling. Proxima Centauri, our nearest stellar neighbor, would be another beach ball located 38,600 kilometers away. That's roughly the distance around Earth's equator. On our scale model, where Earth is a marble, you can hold the nearest star is literally on the other side of the planet. Think about that for a moment. we're not talking about the far side of the solar system. We're not talking about distant galaxies. We're talking about the nearest star, our next door neighbor in cosmic terms. And it's incomprehensibly, overwhelmingly far away. This is what I mean when I say space is mostly empty. The vast cathedral of darkness between the stars isn't just big. It's big in a way that makes our fastest spacecraft look like they're standing still. The Voyager missions, launched in 1977, represent humanity's most distant ambassadors. Voyager 1 has been traveling for 47 years, nearly half a century of continuous motion through space. It's currently moving at about 61,000 kilometers per hour, or 17 kilometers every second. That's faster than Apollo, though not as fast as Parker's peak speed. In those 47 years, Voyager 1 has covered roughly 24 billion kilometers. That sounds immense, and it is by human standards. But in our marble scale model, Voyager has traveled about 200 meters, 2 football fields, in 47 years. At this rate, it would take Voyager another 70,000 years to reach that beach ball, representing Proxima Centauri. In August 2012, Voyager 1 crossed a boundary that no human-made object had ever crossed before it entered interstellar space. After 35 years of travel, it finally left the protective bubble of the sun's influence, the heliosphere, and entered the space between stars. This was a historic moment widely celebrated. But here's the sobering reality: Voyager had only traveled 2,19 light years. Proxima Centauri is 4.2 light years away. Voyager had covered less than 1/2000th of the distance. Communication with Voyager provides another window into these distances. The spacecraft transmits data back to Earth using radio waves, which travel at the speed of light, the fastest speed possible in our universe, as far as we know. And yet those signals take over 22 hours to reach Earth. When mission controllers send a command to Voyager, they wait 22 hours for it to arrive. And if they need a response, they wait another 22 hours for it to come back. A simple conversation, "How are you? I'm fine," takes 44 hours. And this is still within our solar system's edge. Voyager hasn't even left our sun's gravitational influence yet. It would take another 30,000 years of travel to pass through the Oort cloud, the distant sphere of icy bodies that marks the true outer boundary of our solar system's gravitational domain. Let's compare this with another mission, New Horizons. Launched in 2006, New Horizons was the fastest spacecraft ever to leave Earth, at launch departing at about 58,000 kilometers per hour, faster than Voyager's current speed. It had a specific mission: reach Pluto and send back the first close-up images of that distant world. New Horizons crossed the moon's orbit in just 9 hours. Remember, Apollo took 3 days. This gives you a sense of how much faster New Horizons was traveling. Yet even at this impressive speed, it still took 9.5 years to reach Pluto, 9.5 years to reach a world that's still in our solar system, still orbiting our sun, still technically in our cosmic backyard. When New Horizons flew past Pluto in July 2015, it was about 5 billion kilometers from Earth. At that distance, radio signals took 4.5 hours to travel each way. The entire flyby was pre-programmed because there was no way to control the spacecraft in real time. By the time engineers on Earth saw what was happening, it had already happened 4.5 hours ago, and Pluto is close compared to the stars. On our marble scale model, Pluto is that grain of sand kilometers away. Proxima Centauri is 38,600 kilometers distant. The ratio between these distances is roughly 7,700 to 1. If traveling to Pluto takes a decade, traveling to Proxima would take about 77,000 years at the same speed. Here's another way to visualize it. If the entire Milky Way galaxy were shrunk down to the size of the United States, about 5,000 kilometers across, our solar system would be smaller than a dime. The distance from the Sun to Pluto would be about the width of a human hair, and the distance to Proxima Centauri, about 2.5 centimeters. A tiny hop on the galactic scale, but an impossible gulf for us. The universe hasn't just made interstellar travel difficult, it's made it absurd. The distances involved are so large they mock our ambitions. We can send probes to every planet in our solar system. We've landed on asteroids, comets, and moons. We've flown through the tails of comets and skimmed the sun's corona. We've mastered our neighborhood, but the stars remain as distant as they were when our ancestors first looked up and wondered. This raises an obvious question. If we can't carry enough fuel to go fast, how have we managed to reach the outer planets at all? The answer lies in one of the cleverest tricks in orbital mechanics, a cosmic game of billiards called the gravity assist. Imagine you're riding a bicycle, and as a truck passes you going the same direction, you grab onto it briefly. When you let go, you're moving much faster than before. You've stolen some of the truck's momentum. This, in essence, is what a gravity assist does. Except instead of trucks, we're using planets. And instead of grabbing on, we're using gravity. Here's the fundamental problem with space travel. Every bit of speed requires fuel, and fuel has mass, and that mass requires more fuel to accelerate, which requires even more fuel to lift that fuel. It's a vicious cycle known as the tyranny of the rocket equation. The more speed you want, the exponentially more fuel you need. But there's a loophole. Planets are massive objects moving through space at tremendous speeds. Jupiter, for instance, orbits the Sun at about 47,000 kilometers per hour. Saturn moves at about 34,000 kilometers per hour. These planets possess enormous momentum. Momentum that, through careful orbital mechanics, we can borrow. The technique is called a gravity assist or gravitational slingshot, and it works like this. You aim your spacecraft so that it falls toward a planet. As it falls, it accelerates, gaining speed. But instead of hitting the planet, you arrange the trajectory so the spacecraft whips around it and shoots off in a different direction in the planet's frame of reference. The spacecraft comes in at one speed and leaves at the same speed. Energy is conserved. But here's the trick. In the Sun's frame of reference, the spacecraft has gained speed. It's stolen momentum from the planet's orbital motion. The Voyager missions are the masterclass in this technique. Both Voyager spacecraft were launched in 1977 to take advantage of a rare alignment of the outer planets that occurs only once every 176 years. This alignment meant that a single spacecraft could visit multiple planets, using each one to accelerate toward the next. Voyager 2 visited all 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. At each encounter, the spacecraft stole a bit of the planet's orbital momentum. When it flew past Jupiter in July 1979, Voyager 2 was traveling at about 33,000 kilometers per hour relative to the Sun. Jupiter's gravity accelerated it, to over 60,000 kilometers per hour, nearly doubling its speed without burning a drop of fuel. Each subsequent planetary encounter added more speed and changed the trajectory. By the time Voyager 2 flew past Neptune in August 1989, the last planetary encounter before heading into interstellar space, it had visited 4 worlds over 12 years, and its speed had been boosted multiple times through gravity assists alone. Voyager 1 took a different path, visiting only Jupiter and Saturn, but using Saturn's gravity to swing upward out of the plane of the solar system. The spacecraft approached Saturn's giant moon Titan very closely, so close that Titan's gravity deflected Voyager 1's path dramatically upward. This single maneuver gave Voyager 1 enough speed and the right trajectory to become the first human-made object to enter interstellar space. New Horizons provides another excellent example. After launching from Earth at a blistering 58,000 kilometers per hour, already the fastest launch speed ever achieved, it still needed more velocity to reach Pluto in a reasonable time. In February 2007, just over a year after launch, New Horizons flew past Jupiter at a distance of 2.3 million kilometers. During this encounter, Jupiter's immense gravity pulled New Horizons around, accelerating it by an additional 14,000 kilometers per hour. The spacecraft's speed relative to the Sun increased to about 83,000 kilometers per hour. Without this boost, New Horizons would have taken several additional years to reach Pluto. The gravity assist from Jupiter shaved years off the mission. But here's the limitation, and it's a fundamental one. You can only steal momentum that the planets already have. The giant planets orbit the Sun at speeds between 13 and 47 kilometers per second. Through clever trajectory planning, you can extract a substantial fraction of this orbital velocity, perhaps adding 10-20 kilometers per second to your spacecraft's speed through a single encounter. Even if we performed the perfect grand tour, using gravity assists from every planet in the solar system in the most optimal possible configuration, something that might occur once in thousands of years, we might gain a total of about 60 kilometers per second, or roughly 216,000 kilometers per hour. That sounds impressive, and it is compared to chemical rockets alone. But remember, the speed of light is 300,000 kilometers per second. Even the perfect multi-planet gravity assist would give us only 0.02% of light speed. At that velocity, Proxima Centauri would still require over 20,000 years to reach. We've improved from 70,000 years to 20,000 years. A meaningful improvement if you're planning for civilizational timescales, but not much help if you want to get there in a human lifetime. Gravity assists are free speed boosts, but they're limited by the orbital speeds of the planets available to us. And those speeds, while fast by human standards, are crawling by cosmic standards. We're playing billiards with planets to scratch together every bit of velocity we can find, and it's still not nearly enough. Yet despite this limitation, gravity assists have revolutionized deep space exploration. Every mission to the outer planets since Voyager has used them. Cassini used gravity assists from Venus, Earth, and Jupiter to reach Saturn. Juno used an Earth gravity assist to reach Jupiter. The Parker Solar Probe uses repeated Venus flybys to dive ever closer to the Sun. These maneuvers represent some of the most precise navigation ever accomplished. When New Horizons flew past Jupiter mission planners, aimed for a target just 2.3 million kilometers from the planet's center and hit it within a few kilometers after a journey of over a billion kilometers from Earth. The precision required is like throwing a dart from New York and hitting a bullseye in Los Angeles. Gravity assists are elegant, efficient, and absolutely essential for modern space exploration. They're why we can reach the outer planets at all. But they're also a reminder of our limitations. We're scavenging speed from the planets because we can't generate enough on our own. So we've established that even with our cleverest tricks, chemical rockets, and gravity assists, we're still desperately slow by cosmic standards. But what about right now today? What are our current missions actually achieving with these speeds? Let's look at what we're actually doing in space right now with current missions using current technology, because the reality of space exploration today reveals both how far we've come and how far we still have to go. Bepi Colombo is one of the most ambitious missions currently in flight. Launched in October 2018 by the European Space Agency and JAXA, it's heading to Mercury, the closest planet to the Sun. You might think visiting the closest planet would be quick, and you'd be wrong. Bepi Colombo won't arrive at Mercury until December 2025, making the journey 7 years long. Why so long for the nearest planet? Because getting to Mercury is paradoxically harder than going to the outer planets. Mercury sits deep in the Sun's gravity well, and falling toward the Sun means you pick up enormous speed you then have to bleed off to enter orbit. Bepi Colombo addresses this through a complex series of gravity assists: 1 flyby of Earth, 2 of Venus, and 6 of Mercury itself, before finally slowing down enough to be captured into orbit. During different phases of its journey, Bepi Colombo travels at speeds ranging from 40,000 to 60,000 kilometers per hour relative to the Sun, roughly similar to Apollo speeds. 7 years to reach the planet closest to the Sun. Let that sink in. We're using some of our most sophisticated orbital mechanics, and it still takes 7 years to visit our nearest planetary neighbor. Consider Juno currently orbiting Jupiter. When it's at perihelion, the closest point in its highly elliptical orbit, Juno screams past Jupiter at about 265,000 kilometers per hour relative to the planet. That's incredibly faster than most interplanetary spacecraft. But here's the key detail that's its speed relative to Jupiter. In the Sun's reference frame, Juno is moving much slower, having fallen into Jupiter's gravity well. And despite this high orbital speed, Juno took 5 years to reach Jupiter from Earth, launching in August 2011 and arriving in July 2016. The Perseverance rover, which landed on Mars in February 2021, made the journey in about 7 months, traveling at approximately 39,600 kilometers per hour during the cruise phase. 7 months to reach Mars at closest approach. And once on the surface, Perseverance trundles along at a top speed of about 0.15 kilometers per hour, roughly 150 meters per hour. That's slower than a leisurely walking pace. A human could easily outwalk the rover. Why so slow on the surface power and safety? The rover is powered by a radioisotope thermoelectric generator that produces about 110 watts, roughly equivalent to a household light bulb. Every action must be carefully planned and executed. The rover must analyze terrain, plan its path, and move cautiously to avoid hazards. Speed is sacrificed for reliability. The contrast is striking. We can send Perseverance across interplanetary space at 40,000 kilometers per hour, but once it arrives, it moves slower than a human walking. This reveals something important about space travel. Crossing the distances is one challenge, but operating at the destination is another entirely. When we look at mission durations across our solar system with current technology, a clear pattern emerges. A typical journey to Mars requires 7 to 9 months of travel time. Reaching Jupiter, even with a gravity assist, demands 5 to 6 years. That's how long it took Juno to make the journey. Saturn lies even further, requiring about 7 years, as Cassini demonstrated utilizing multiple gravity assists along the way. Pluto, visited by New Horizons after a Jupiter gravity assist, needed 9.5 years to reach. Even Mercury, our nearest planetary neighbor, requires 7 years for Bepi-Colombo's complex trajectory with multiple planetary flybys. And reaching the edge of our solar system, Voyager has been traveling for over 35 years and is still going, having only recently entered interstellar space. Notice the pattern. Even with optimal trajectories and gravity assists, reaching the outer planets requires patience, measured in years, not weeks or months. And these are destinations within our solar system, our cosmic backyard. The fastest mission profile we've ever executed was New Horizons to Pluto, using the most powerful rocket available and a Jupiter gravity assist. We covered the distance in 9.5 years. That represents close to our speed limit for reaching the outer solar system with current technology. Could we go faster? Perhaps marginally, but not dramatically. We're already using the most powerful rockets and optimal trajectories. What about human missions? The International Space Station orbits at about 27,600 kilometers per hour, fast enough to circle the Earth every 90 minutes. But that's orbital speed in low Earth orbit. To go anywhere else, humans would need life support for months or years. The longest single spaceflight was 437 days by Valery Polyakov aboard the Mir space station. Mars missions would require 18 to 24 months total, including surface time, and that's pushing the limits of what we know about long-duration spaceflight effects on the human body. When we examine the full spectrum of human achievements in space velocity, a fascinating hierarchy emerges. The Parker Solar Probe holds the absolute record as the fastest human-made object ever created, reaching a peak velocity of 692,000 kilometers per hour during its closest approaches to the Sun. For typical interplanetary missions, the workhorses of our exploration fleet, speeds generally range between 40,000 and 80,000 kilometers per hour, depending on the destination and trajectory. The human speed record remains frozen at 39,897 kilometers per hour, set by the Apollo 10 crew in 1969, and still unbroken after more than half a century. The International Space Station, humanity's continuously inhabited outpost in space, maintains a steady orbital speed of 27,600 kilometers per hour as it circles the Earth every 90 minutes. And the fastest launch speed ever achieved belongs to New Horizons, which departed Earth at 58,000 kilometers per hour on its way to Pluto, making it the speediest spacecraft to ever leave our planet. These speeds represent the cutting edge of what we can achieve right now today. They are sufficient for exploring our solar system, though missions take years or decades. They allow us to visit every planet land on asteroids and moons and send data back across billions of kilometers. We've mastered the solar system, slowly, painstakingly, but we've mastered it. Every planet has been visited. We've landed on asteroids, comets, and moons. We have orbiters, landers, and rovers at multiple destinations. We've sent probes into interstellar space. Yet these same speeds are completely, utterly insufficient for interstellar travel. At our absolute fastest, Parker's 692,000 kilometers per hour, Proxima Centauri still requires 6,300 years to reach. At typical mission speeds of 40,000 to 80,000 kilometers per hour, the journey would take 70,000 to 115,000 years. We're not talking about a small gap that better engineering might close. We're talking about a fundamental gulf. Our fastest spacecraft are moving roughly 10,000 times too slowly for practical interstellar travel. The stars remain impossibly distant, mocking our ambitions with their remoteness. We can cross our solar system, but crossing to the next star that remains beyond us by such a vast margin that it almost defies comprehension. This naturally raises the most important question. Why? Why can't we go faster? What is it about physics, about the nature of space, and motion, and energy that makes speed so incredibly difficult to achieve? That's what we need to explore next. To understand why we can't go faster, we need to confront one of the most fundamental and unforgiving laws in all of spaceflight, the rocket equation. It's not just an engineering challenge, it's a mathematical tyrant that rules over every spacecraft we've ever built. Here's the core problem, and it's beautifully simple, yet devastatingly cruel. To move forward in space, you must throw something backward. There's no air to push against, no ground to push off, from no medium to grip. Newton's third law operates in its purest, most uncompromising form. Every kilogram of spacecraft you want to accelerate requires you to expel mass in the opposite direction. And here's where the tyranny begins. That mass you're expelling, you had to carry it with you. And to carry that mass, you needed fuel to accelerate it. And to carry that fuel, you needed more fuel to lift that fuel. It's a vicious, inescapable spiral. Let me give you some numbers that reveal just how brutal this equation becomes. To double your spacecraft's speed, you don't need twice as much fuel. You need roughly 10 times as much fuel. To triple your speed, you're looking at perhaps 100 times more fuel. The relationship isn't linear. It's exponential, and it punishes ambition with mathematical precision. Consider the Apollo missions again. The mighty Saturn V rocket stood 111 meters tall and weighed 2,800 tons at liftoff. Of that enormous mass, about 2,500 tons, nearly 90%, was fuel. The actual Apollo spacecraft and its crew capsule, just 50 tons less than 2% of the total. Think about that ratio for a moment. To send 3 men to the moon, and back we needed a fuel tank the size of a 36-story building, and the payload was barely a rounding error in the total weight. And what did all that fuel buy us? A speed of 40,000 kilometers per hour, enough to reach the moon in 3 days. Impressive by Earth standards, but we've already seen how inadequate it is for anything beyond our immediate neighborhood. Now, here's where the mathematics becomes truly cruel. Chemical rockets, the type we've always used, work by combining fuel and oxidizer in a combustion chamber, heating the mixture to thousands of degrees and expelling it through a nozzle. The hotter you can make that exhaust, and the lighter the molecules you're throwing out, the faster your rocket can go. The theoretical maximum for hydrogen-oxygen combustion, the most energetic chemical reaction we can practically use, is an exhaust velocity of about 4,500 meters per second, and we're already achieving about 400 meters per second with our best engines. That's 98% of the theoretical maximum. There is no breakthrough coming in a chemical rocket performance. We've hit the wall. Not an engineering wall, but a wall imposed by the laws of chemistry and physics themselves. The energy stored in chemical bonds can only propel atoms so fast, and we're already extracting nearly all of it. Let me show you what this means with a thought experiment that reveals the absurdity of trying to reach interstellar speeds with chemical rockets. Suppose you want to accelerate just 1 kilogram, about the weight of a liter of water, to 1% of the speed of light, using a perfectly efficient hydrogen-oxygen rocket. How much fuel would you need? The answer is staggering 10 to the power of 1,400 tons. That's a number so large it has no physical meaning. To write it out, you'd need 1,400 zeros after the 1. For comparison, the observable universe contains roughly 10 to the power of 80 atoms. The fuel required for this modest velocity increase exceeds the number of atoms in the universe by a factor so large it cannot be meaningfully expressed. The rocket equation hasn't just made this difficult, it's made it mathematically absurd. This is why every spacecraft we've ever built is mostly fuel tank. The space shuttle's external tank dwarfed the orbiter. The Saturn V was essentially 3 fuel tanks stacked on top of each other with a tiny capsule at the tip. Modern rockets launching satellites look like pencils, thin payloads perched atop massive fuel cylinders. We're not building spacecraft as much as we're building flying fuel depots that happen to carry a small payload. And here's another cruel aspect staging. We discovered early that the most efficient way to fight the rocket equation is to throw away empty fuel tanks as we go. The Saturn V had 3 stages each discarded after its fuel was exhausted. Why? Because carrying an empty fuel tank is wasted mass, and the rocket equation punishes wasted mass exponentially. So we built rockets that throw away most of themselves during flight. But staging only helps so much. Even with optimal staging, even with the most efficient chemical propellants, even with perfect engineering, we run into that hard ceiling at around 4,500 meters per second exhaust velocity. To go meaningfully faster, fast enough to make interstellar travel feasible, we need to escape chemistry altogether. The rocket equation also explains why we can't just keep accelerating. The Apollo spacecraft performed one large burn to escape Earth, then coasted for 3 days. Why not keep the engines running the whole way, constantly accelerating? Simple. They didn't carry nearly enough fuel. To maintain thrust for even an hour would have required fuel tanks many times larger than the Saturn V already was. The spacecraft would have become so massive that no rocket could have lifted it off the ground. So they did the only thing possible: burn hard for a few minutes, then coast. This is the reality of all our interplanetary missions. Quick burns, followed by long coasts. We're not actually flying through space. We're falling along carefully calculated trajectories, giving ourselves 1 or 2 hard shoves, and then letting momentum and gravity do the rest. It's elegant in its simplicity, but it's also an admission of limitation. We can't carry enough fuel for continuous acceleration, so we don't try. There's a concept in rocketry called delta V budget, the total change in velocity a spacecraft can achieve with its fuel supply. Every mission is a careful accounting of velocity changes, how much to escape Earth, how much for course corrections, how much to enter orbit at the destination, how much to return. Mission planners squeeze every meter per second out of their fuel, like accountants scrutinizing expenses. There's never enough delta V, never enough fuel to do everything you'd like to do. The fastest chemical rocket we've ever launched, New Horizons, used the most powerful rocket available, was deliberately designed to be as light as possible, carried minimal instruments, and had no capability to slow down at Pluto. It was optimized entirely for speed, and even then, it only reached 58,000 kilometers per hour at launch. To go meaningfully faster would have required a rocket several times larger, and at some point you hit practical limits. Launch pads can only support so much weight. Rockets can only be built so large. So here we are trapped by mathematics as much as by engineering. The rocket equation doesn't care about our ambitions or our ingenuity. It simply says, if you want to go faster, you need exponentially more fuel, and eventually you're trying to carry more fuel than physics allows. Chemical rockets brought us into space, took us to the moon, and let us explore the solar system. But for going faster, truly faster, we need something fundamentally different. So, if chemistry has reached its limits, what about using electricity instead? Can we escape the tyranny of chemical combustion by accelerating particles with electric fields? The answer is yes, but with a trade-off so severe, it changes everything about how we think about spaceflight. Ion drives represent a fundamentally different approach to propulsion, and they've revolutionized solar system exploration, even though they're counterintuitive in almost every way. Here's how an ion drive works. Instead of violent chemical explosions, you use electricity to strip electrons from atoms, typically xenon or argon, creating positively charged ions. Then you use electric fields to accelerate these ions to extremely high velocities and expel them out the back of the spacecraft. The physics is the same as chemical rockets. Throw mass backward to move forward, but the execution is radically different. Chemical rockets expel their exhaust at about 4,500 meters per second. Ion drives, they can accelerate ions to 30,000 to 90,000 meters per second, 10 times faster than chemical exhaust. This is huge because the rocket equation cares deeply about exhaust velocity. The faster you can throw mass out the back, the less mass you need to carry. An ion drive can achieve the same velocity change as a chemical rocket while using 10 times less propellant. Sounds perfect, right? Here's the catch. The thrust produced by an ion drive is absurdly small. If you put a typical ion thruster on a scale, its thrust would barely register, roughly equivalent to the weight of a sheet of paper. NASA's Dawn spacecraft, which pioneered long-duration ion propulsion, had thrusters producing about 90 millinewtons of force. A millinewton is 1,000th of a newton, and a newton is already a small force, about the weight of a small apple. Let me put this in perspective. If you were standing next to the Dawn spacecraft when its ion drive was running, you could stop it with your hand. The thrust is so gentle that a human could overpower it, and yet over years of continuous operation, this whisper of thrust accumulated into enough velocity to visit both the asteroid Vesta and the dwarf planet Ceres, something no chemical rocket could accomplish. Dawn launched in September 2007 and operated its ion drive for a cumulative total of 5.9 years. That's not mission duration, that's actual engine on time. Think about that. Nearly 6 years of continuous thrusting. The ion drive ran for so long that it fundamentally changed how we think about propulsion. Chemical rockets burn for minutes or hours. Ion drives burn for years. During those years, Dawn gradually spiraled its way through the solar system. It couldn't launch from Earth with ion propulsion. The thrust is far too weak to overcome gravity. So, it launched on a conventional rocket. Then once, in space, it fired up its ion drive and began a patient, years-long acceleration. It reached Vesta in July 2011, spent over a year studying it, then fired up the ion drive again, and spent another 2.5 years spiraling to Ceres, arriving in March 2015. The mission accomplished something impossible. For chemical rockets, it entered orbit around one world, studied it left, and then entered orbit around a second world. Chemical rockets don't have enough fuel to orbit 2 destinations. They must choose flyby, multiple targets, or orbit one. Dawn didn't have to choose. Its highly efficient ion propulsion gave it enough delta V to orbit both worlds with fuel to spare. But let's be clear about what patient means. Dawn's top speed was around 70,000 kilometers per hour relative to the Sun. Respectable, but not record-breaking. The journey to Vesta took nearly 4 years. Then, the journey from Vesta to Ceres took another 2.5 years. Total mission time, 11 years, for destinations that are relatively close by solar system standards. This is the trade-off of ion propulsion, incredible efficiency, but glacial acceleration. Currently, several missions are using ion propulsion to great effect. Bepi Colombo, heading to Mercury, uses 4 ion thrusters to slowly reshape its orbit over 7 years. Psyche, launched in 2023 toward a metal asteroid, uses Hall effect thrusters, a variation on ion drive technology. These missions would be impossible. With chemical rockets alone, they require too much velocity, change too many orbital maneuvers. Ion drives make them feasible. But here's what ion drives can't do. They can't take humans anywhere. The problem is time. A mission to Mars using ion propulsion might take several years instead of 7 months. Humans need food, water, oxygen, and protection from radiation for the entire journey. The longer the trip, the more life support you need, and the more massive your spacecraft becomes. At some point, the mass of life support overwhelms any efficiency advantage from ion propulsion. There's also the power problem. Ion drives need electricity, lots of it. Dawn used solar panels that generated about 10 kilowatts of power at Earth's distance from the Sun. That's enough for several ion thrusters. But if you want more thrust to accelerate faster, you need more power, which means larger solar panels, or nuclear reactors, which means more mass. And suddenly, you're back to fighting the rocket equation. For robotic missions to the outer planets, ion drives are revolutionary. For human missions or for achieving truly high speeds, they're still not enough. A realistic maximum speed for an ion drive spacecraft might be around 100,000 kilometers per hour, better than most chemical rockets, but still requiring tens of thousands of years to reach even the nearest star. NASA has been testing more advanced ion thrusters. The next ion thruster, NASA's evolutionary xenon thruster, has operated continuously in ground tests for over 5 years, demonstrating remarkable reliability. It produces slightly more thrust than Dawn's engines, while using fuel even more efficiently. But we're talking about incremental improvements, not revolutionary leaps. An ion drive twice as powerful as Dawn's would still produce thrust you could stop with your hand. There's also VASIMR, Variable Specific Impulse Magnetoplasma Rocket, a concept that uses radio waves to heat argon gas into a plasma, then accelerates it with magnetic fields. It's essentially an ion drive on steroids. With a clever twist, you can adjust it to produce either high thrust or high efficiency, like a transmission in a car. In high thrust mode, it could potentially cut Mars' travel time from 7 months to 39 days. In high efficiency mode, it could achieve even better fuel economy than conventional ion drives. But VASIMR faces its own challenge. It needs enormous amounts of power, likely from a nuclear reactor, producing hundreds of kilowatts or even megawatts. That reactor would be heavy, complex, and expensive. VASIMR has been tested extensively on the ground, but hasn't flown in space yet. It remains a promising technology for the future, not a solution for today. The fundamental limitation remains electric propulsion. Whether ion drives, Hall thrusters, or VASIMR can only accelerate you as fast as your power source allows. Solar panels work well near the sun, but become useless in the outer solar system, where sunlight is faint. Nuclear reactors are heavy and complex. Until we develop power sources that are both lightweight and incredibly powerful, electric propulsion will remain constrained. So ion drives have expanded our capabilities dramatically within the solar system, enabling missions that would otherwise be impossible. They're patient marathon runners compared to the sprinting chemical rockets. But for reaching the stars, even with perfect efficiency, even with unlimited power, they would still take thousands of years. We've escaped the inefficiency of chemical combustion, but we haven't escaped the fundamental constraint. We're still accelerating tiny amounts of mass to high speeds, and doing that requires either enormous amounts of energy or enormous amounts of time. The tyranny of the rocket equation persists even with our cleverest engineering. We can improve efficiency, we can run engines longer, we can be smarter about trajectories, but we're still bound by the fundamental physics of momentum and energy. To go truly fast, we need approaches that don't rely on throwing mass backward at all. But what if we could ride on something that's already moving at the ultimate speed? Light itself. Could we harness the gentle pressure of photons to push us through space? The idea sounds almost too elegant. Instead of carrying tons of fuel, why not sail on sunlight itself? It seems like science fiction, but the physics is real. Light, though it has no mass, carries momentum. When photons strike a reflective surface and bounce off, they transfer a tiny push. It's like trying to move a battleship by throwing ping pong balls at it. Except in the vacuum of space, where there's no friction and no air resistance, those microscopic pushes can actually accumulate into meaningful thrust. And we've proven it works. This isn't theory anymore. It's demonstrated technology. In 2010, Japan's Ikaros, interplanetary kite craft, accelerated by radiation of the sun, became the first spacecraft to successfully demonstrate solar sailing beyond Earth orbit. The mission deployed a square sail 14 meters on each side, made of polyimide film just 7.5 micrometers thick. That's thinner than a human hair. As this gossamer mirror caught sunlight, Ikaros began to accelerate, pushed by nothing but photons. The spacecraft flew to Venus, demonstrating along the way that solar sailing actually works in deep space. Ikaros added roughly 30,000 kilometers per hour to its velocity using only light pressure, no fuel burned, no propellant expelled, just the gentle but persistent push of sunlight against an ultra-thin sail. Then, in 2019, the Planetary Society's LightSail 2 took the concept further. This tiny CubeSat deployed a 32 square meter sail in Earth orbit and proved something crucial. You can not only sail on sunlight, you can steer. By changing the sail's orientation, LightSail 2 controlled its trajectory, raising its orbit purely through photon pressure. The spacecraft demonstrated that solar sails aren't just passive devices drifting on cosmic winds. They're controllable, steerable propulsion systems. Here's what makes solar sails so tantalizing. They need no fuel whatsoever. Once deployed, they can continue accelerating for years, decades, even centuries. The sun is always shining, providing an endless river of photons. There's no fuel budget to manage, no propellant to run out of, no moment when your engines die and you're left coasting. In principle, a solar sail could accelerate continuously for as long as it remains intact and in sunlight. With unlimited time and a large enough sail, you could theoretically reach very high speeds. Keep accelerating for years, and those tiny pushes accumulate. This is the dream fuel-free interstellar travel powered by starlight itself. But here's where the dream crashes into brutal reality. The pressure exerted by sunlight is incredibly, almost incomprehensibly weak. At Earth's distance from the sun, a perfectly reflective surface experiences a force of about 9 micronewtons per square meter. A micronewton is 1/1,000,000th of a newton, and a newton itself is already a small force, roughly the weight of a small apple. So we're talking about pressure measured in millionths of the weight of an apple spread across a square meter. And it gets worse as you travel away from the sun. Light intensity follows the inverse square law. Double your distance, and the intensity drops to 1/4. At Mars, solar pressure has already dropped by 44% compared to Earth. At Jupiter's orbit, it's down to just 4% of Earth intensity, 25 times weaker. By the time you reach Saturn, you're at barely 1%. This creates a cruel paradox. Solar sails work best close to the sun, where light is intense, but that's also where you're deep in the sun's gravity well. As you try to climb out toward the outer solar system and beyond, the very light pressure you depend on is weakening exponentially with every kilometer traveled. You're trying to climb a hill that gets steeper as the wind pushing you upward gets weaker. The engineering challenges are staggering. To generate meaningful thrust with such weak pressure, you need enormous sail area. We're not talking about sails measured in meters. To achieve speeds useful for interstellar travel, you'd need sails measured in kilometers. A solar sail, several kilometers on each side, made of material thinner than tissue paper, yet strong enough not to tear under its own deployment stresses or from micrometeorite impacts. The material science alone is daunting. You need something incredibly thin to keep mass low, incredibly reflective to maximize photon momentum transfer, and incredibly strong to survive years or decades in space. The sail must fold compactly for launch, then unfurl reliably once in space. It must maintain its shape without wrinkles or tears, and it must do all this with a support structure that's also extraordinarily lightweight. Current materials technology simply isn't there yet. We can build small sails, tens of square meters, that demonstrate the concept, but scaling to hundreds or thousands of square meters while maintaining structural integrity, that remains an unsolved engineering problem. So, what speeds can we actually achieve with current or near-term technology? With the sail sizes we can realistically build today, tens to perhaps hundreds of square meters, and with the material limitations we face, solar sails might reach 30,000 to 50,000 kilometers per hour after years or even decades of continuous acceleration. That's comparable to our chemical rockets, just achieved much more slowly and without fuel. But here's the crushing reality: at 50,000 kilometers per hour, Proxima Centauri still requires more than 30,000 years to reach. We've eliminated the fuel problem, but haven't solved the speed problem. We've traded one limitation for another. Instead of running out of fuel, we're stuck with acceleration so gentle that useful speeds require impossibly long timescales. Solar sails have found their niche in our space exploration toolkit. They're perfect for certain specialized missions, spacecraft that need to maintain precise orbits without using fuel missions that can afford years of patient acceleration trajectories that chemical rockets can't accomplish efficiently. Japan is planning missions to Jupiter's Trojan asteroids using solar sails combined with ion propulsion. These missions demonstrate real utility. But as a solution for fast interstellar travel, solar sails face the same fundamental limitation as everything else we've discussed. The energy available is too small, the distance is too vast, the speeds achievable too slow for human-scale timescales. They're elegant, they're fuel-free, and they genuinely work. But they don't solve the speed problem. After decades of acceleration, you're still crawling by cosmic standards, and the nearest stars remain tens of thousands of years away. The universe has imposed a harsh constraint. Light pressure is real, but weak, and that weakness means solar sails alone cannot bridge the interstellar gulf. So, if gentle pushes from photons aren't enough, what about the most concentrated energy source humanity has ever harnessed? What if we could tap the power locked inside atoms themselves? Nuclear energy represents a quantum leap in power density. A single kilogram of uranium undergoing fission releases roughly 3 million times more energy than a kilogram of chemical fuel. Surely, if we could harness that for propulsion, we'd finally break free from our speed constraints. And the answer is yes, but with complications that have kept most nuclear propulsion concepts theoretical for over half a century. Let's start with the most developed concept: nuclear thermal rockets. The principle, straightforward and elegant. Instead of burning chemical fuel to heat your propellant, you use a nuclear reactor. You pump liquid hydrogen through channels in the reactor core, heating it to 2,500 Kelvin or higher, far beyond what chemical combustion can achieve. Then you expel that superheated hydrogen through a nozzle just like a conventional rocket. The hotter your exhaust, the faster it exits, and nuclear fission can achieve exhaust velocities around 9,000 meters per second, roughly double what chemical rockets manage. That doubling matters immensely. Remember, the rocket equation: better exhaust velocity means you need less propellant for the same mission. A nuclear thermal rocket could slash Mars transit times from 7 to 9 months down to 3 or 4 months. For human Mars missions, this is genuinely revolutionary. Less time in space means less radiation exposure. Less time in zero gravity, causing bone and muscle loss. Fewer supplies needed, lower mission risk. 3 months instead of 9 months could be the difference between practical Mars exploration and missions at the edge of human endurance. NASA is actively developing this technology right now. They're testing new reactor designs, developing fuel elements that can withstand extreme temperatures, solving the engineering challenges of operating a nuclear reactor in space. Ground tests could begin in the early 2030s. Nuclear thermal propulsion isn't science fiction, it's engineering work in progress. But here's the limitation: even doubling exhaust velocity only gets you so far. With nuclear thermal rockets, you might achieve speeds of 100,000 to 150,000 kilometers per hour for interplanetary missions. That's excellent for Mars, Jupiter, even Saturn. It transforms solar system exploration, but Proxima Centauri, still 15,000 years away. Nuclear thermal gives us better performance within our cosmic neighborhood, but doesn't solve interstellar travel. Then there's nuclear electric propulsion, a different approach that combines the best of two worlds. You use a nuclear reactor to generate electricity, then use that electricity to power ion drives. This gives you the high efficiency of electric propulsion with a power source that doesn't depend on sunlight. Unlike solar panels that become useless in the outer solar system, a nuclear reactor provides steady power anywhere. The concept is compelling. With enough electrical power, you could run multiple high-thrust ion engines, continuously accelerating patiently but persistently over years. You're not limited by how much sunlight reaches your solar panels. You could maintain thrust all the way to the outer planets and beyond. This is where VASIMR becomes interesting. The variable specific impulse magnetoplasma rocket is essentially an advanced electric thruster that uses radio waves to heat argon gas into plasma, reaching millions of degrees, then accelerates it magnetically. Here's the clever part: VASIMR has a gear shift. You can adjust it to produce high thrust when you need acceleration, or high efficiency when you want to conserve propellant. With a powerful enough reactor, say one generating a megawatt of electricity, a VASIMR-equipped spacecraft could theoretically reach Mars in just 39 days instead of 7 months. That rapid transit would dramatically reduce crew radiation exposure and could enable regular traffic between Earth and Mars. But we haven't built such systems yet. VASIMR has been tested extensively on the ground, demonstrating that the plasma physics works, but it's never flown in space. The reactor needed would be massive and complex. We're talking about nuclear systems generating hundreds of kilowatts, or even megawatts orders of magnitude. more powerful than anything ever operated in space. The engineering challenges are substantial heat rejection and vacuum shielding for the crew long-term reliability safety during launch and operation. Even if nuclear electric propulsion works perfectly and we build those powerful reactors, we're still looking at speeds around 150,000 to 200,000 kilometers per hour for realistic missions. Better than chemical or even nuclear thermal, certainly, but still requiring 10,000 years or more to reach Proxima Centauri. We've improved the numbers, but not changed the fundamental equation. Now let's talk about the most audacious nuclear concept ever seriously studied, Project Orion. Proposed in the late 1950s and studied into the 1960s, Orion wasn't subtle. The concept was to literally detonate nuclear bombs behind your spacecraft using the explosion to push an enormous shock absorber plate, which would transfer momentum to the vehicle. It sounds completely insane, but the physics is absolutely sound. You'd eject a nuclear device behind the spacecraft, ranging from small tactical nukes to multi-megaton warheads, and detonate it at a carefully calculated distance. The explosion would vaporize and ionize material on the pusher plate, creating a plasma that transfers momentum. Massive shock absorbers would smooth out the impulse, turning the violent explosion into steady acceleration for the crew. The performance would be spectacular. Project Orion designs indicated you could achieve 3 to 5% of light speed, roughly 30 million kilometers per hour. At that velocity, Proxima Centauri becomes reachable in 100 to 150 years. Not a human lifetime, but a generational timescale we can at least comprehend. A well-designed generation ship could carry thousands of people with multiple generations born and dying en route. Orion wouldn't be small. The largest designs called for spacecraft weighing 4,000 tons or more, assembled in orbit propelled by hundreds or thousands of nuclear devices. But unlike every other propulsion concept, Orion could genuinely enable interstellar travel within extended but comprehensible human timescales. So why didn't we build it? In 1963, the Partial Nuclear Test Ban Treaty prohibited nuclear explosions in space atmosphere or underwater. That was the immediate political death of Orion. But there are deeper issues. Launching thousands of nuclear weapons is environmentally and politically catastrophic. Even testing such a system would violate international treaties and face massive opposition. The radiation exposure for crews, while potentially manageable, would be significant. Project Orion remains the highest performance propulsion system we've ever designed in engineering detail. The physics works. The engineering is challenging, but not impossible. What stops us isn't technical capability. It's politics, treaties, and the reasonable reluctance to conduct nuclear explosions in space. As long as those constraints exist, Orion remains a fascinating, might have been, not a realistic path forward. There's one more nuclear concept worth mentioning: fusion propulsion. If we could harness the fusion of hydrogen into helium, the same process powering the sun, we could achieve exhaust velocities of 3 to 5% of light speed directly without needing bombs. Fusion releases even more energy per unit mass than fission and produces far less radioactive waste. But here's the problem. We still haven't achieved sustained fusion power on Earth. Every fusion reactor ever built consumes more energy than it produces. We're making progress, but practical fusion power remains decades away, and fusion propulsion even further beyond that. So, where does nuclear propulsion leave us? It offers genuine improvements. Factor of 2 for thermal systems, potentially factor of 10 for electric systems with powerful reactors. These improvements matter immensely for solar system exploration. A nuclear thermal rocket makes Mars missions practical and safe. Nuclear electric with Vasimir could revolutionize how we explore the outer planets. But for interstellar travel, even nuclear power isn't enough unless we're willing to use it in extreme ways, like Project Orion. And even then, we're talking century-long journeys. The stars remain distant. Their remoteness, a challenge that even splitting atoms cannot fully overcome. We've tried chemistry, electricity photons, and nuclear fission. We've explored every form of propulsion we can actually build. Surely by now, we must recognize just how desperately, overwhelmingly slow we truly are. Let me show you the numbers that reveal just how inadequate our speeds truly are. Our fastest spacecraft ever, the Parker Solar Probe, reaches 692,000 kilometers per hour at peak velocity. That sounds extraordinary, and by human standards, it is. But for practical interstellar travel, reaching another star within even a few centuries, we would need speeds of 70 to 100 million kilometers per hour. We're not talking about being twice as slow or 10 times too slow. We're talking about being 100 to 150 times too slow. And that's just to make the journey in a few centuries, still far longer than any human lifetime. Let me put this in terms that might help you viscerally understand our predicament. If we shrink the distance to Proxima Centauri down to 1.6 kilometers, a comfortable walk, then our fastest spacecraft Parker is moving at 1.5 meters per hour. Think about that. 1.5 meters per hour. That's slower than grass growing. And you know what else moves? At about 1.5 meters per hour, a garden snail crawls at roughly 0.9 meters per hour under favorable conditions. On the cosmic distance scale, where Earth to Proxima Centauri equals 1.6 kilometers, our fastest spacecraft is barely outpacing a garden snail. We're not racing toward the stars. We're crawling at a pace that makes gastropods look speedy. This isn't metaphor. This is the brutal mathematical reality of our situation. Humanity's greatest achievement in speed, viewed on the scale of interstellar distances, moves like a snail. Let me give you some real examples that hammer this point home. Consider Hayabusa 2, Japan's asteroid sample return mission. It launched in 2014, spent 3.5 years traveling to reach the asteroid Ryugu, collected samples, then took another 2.5 years to return. Total mission duration, 6 years. Total distance, traveled 5.2 billion kilometers. That sounds immense. Average speed about 100,000 kilometers per hour. 6 years. To visit a rock in our own solar system, not even a planet, an asteroid, a chunk of debris orbiting relatively close to Earth in cosmic terms. 6 years for a round trip to a stone in our backyard. Or take OSIRIS-REx, NASA's equivalent mission. Launched in 2016, reached asteroid Bennu. In 2018, spent time studying it and collecting samples, then returned those samples to Earth in 2023. 7 years total for a round trip to an asteroid that periodically comes near Earth. 7 years to visit what is, astronomically speaking, a next-door neighbor. These missions represent remarkable engineering achievements. They demonstrated our ability to navigate precisely across billions of kilometers, rendezvous with small bodies, and return samples. They advanced our understanding of the solar system's formation. But they also reveal something sobering. We spent years reaching small rocks that aren't even proper planets that orbit within our immediate cosmic vicinity. If it takes 6 or 7 years to reach nearby asteroids, what hope do we have for stars? Here's another way to understand our situation. New Horizons took 9.5 years to reach Pluto, still within our solar system, still orbiting our sun, still in what we might generously call our cosmic backyard. Bepi Colombo will take 7 years to reach Mercury, the planet literally closest to the sun. A typical Mars mission requires 7 to 9 months of travel time. We measure our journeys within the solar system in months and years, and the solar system is tiny compared to interstellar distances. If reaching Mars takes 7 months and reaching Pluto takes 9 years, how long does reaching the next star take? Not decades, not centuries, tens of thousands of years at our current speeds. The pattern is unmistakable. The solar system is within reach, but barely. We can get to Mars in months, the outer planets in years, the solar system's edge in decades. We've mastered, slowly, painstakingly, our immediate neighborhood. Every planet has been visited by robotic probes. We have orbiters, landers, and rovers at multiple destinations. We've accomplished extraordinary things, but the stars remain impossibly, overwhelmingly, mockingly out of reach. At our absolute fastest, Parker's 692,000 kilometers per hour, Proxima Centauri still requires 6,300 years. At typical interplanetary mission speeds of 40,000 to 80,000 kilometers per hour, the journey stretches to 70,000 to 115,000 years. These aren't timescales where better engineering helps. These aren't gaps that clever mission planning can bridge. We're not talking about needing to be twice as fast or even 10 times as fast. We need to be roughly 10,000 times faster than our typical missions to make interstellar travel feasible within human-relevant timescales. 10,000 times. That's not an incremental improvement. That's not something better fuel efficiency or lighter materials will solve. That's a fundamental gulf between what we can do and what we would need to do. Think about it this way. If you could instantly improve every aspect of our propulsion technology by a factor of 10 times more efficient fuel, 10 times lighter materials, 10 times better engines, we would still need another factor of 1,000 improvement beyond that. And then we'd merely be able to reach Proxima in a few decades instead of millennia. The universe hasn't just made interstellar travel difficult, it's made it so overwhelmingly difficult that our current capabilities look like the first fumbling steps of a species that has barely learned to leave its cradle. We can cross our solar system, but crossing to the next star remains beyond us by such a vast margin that it almost defies comprehension. Chemical rockets brought us into space, but have hit their theoretical ceiling. Ion drives improved efficiency, but produce thrust too weak for rapid transit. Solar sails offer fuel-free acceleration, but even weaker pressure. Nuclear thermal doubles our exhaust velocity, but still leaves us thousands of years from the nearest star. Nuclear electric with optimistic assumptions might give us factor of 10 improvements. Even nuclear pulse propulsion, detonating bombs, would require centuries. We've explored every propulsion method we can realistically build, with current or near future technology, and none of them, none, come close to solving the speed problem. The gap isn't engineering, it's fundamental. The distances are so vast and our speeds so limited that the stars might as well be in another universe. We've mastered our solar system. We can send probes anywhere within it, though missions take years or decades. We've demonstrated remarkable capability within our neighborhood, but the universe is vast beyond human comprehension, and our fastest speeds barely register on cosmic scales. We're snails crawling along a vast plain with the next island 10,000 times farther than we can travel in our entire existence. That's the truth we must confront. Not pessimism, but reality. The stars are distant, and we are slow, desperately, overwhelmingly, almost incomprehensibly slow. So, if propulsion limitations make us this slow, what other barriers stand between us and the stars? What happens to spacecraft and their crews when they try to move at the speeds we'd actually need? When we talk about speed in space, we're really talking about energy. And energy, it turns out, is perhaps the most unforgiving constraint of all. Because the relationship between speed and energy follows a brutal mathematical law that punishes every additional increment of velocity with increasingly savage energy demands. Here's the fundamental physics, and you need to understand this to grasp why interstellar travel is so devastatingly difficult. Kinetic energy, the energy of motion, increases with the square of velocity. The formula is simple energy equals 1/2 times mass times velocity squared. But the implications are catastrophic for our ambitions. What this means in practical terms, if you want to double your speed, you don't need twice as much energy. You need 4 times as much. Want to go 3 times faster? You need 9 times the energy. 10 times faster? You need 100 times the energy. This isn't a linear slope where each step costs the same. It's an exponential curve that grows steeper with every meter you climb. Let me give you some numbers that reveal just how quickly this becomes impossible. To accelerate just 1 kilogram, about the weight of a liter of water, to 1% of light speed requires roughly 45 trillion joules of energy. To put that in perspective, that's the energy released by a small nuclear bomb. 1 kilogram, 1% of light speed, 1 nuclear bomb's worth of energy. And remember, 1% of light speed still means a journey to Proxima Centauri, taking more than 400 years. Now let's scale up. A modest spacecraft might weigh 1,000 kilograms. To accelerate it to just 1% of light speed would require the energy of 1,000 nuclear bombs. Think about that. 1,000 nuclear detonations worth of energy just to push a small spacecraft to a speed that's still far too slow for practical interstellar travel. But it gets exponentially worse. To reach 10% of light speed, where the journey might take just 40 years within a human career span, you'd need roughly 4,500 trillion joules per kilogram. That's the energy output of a large power plant running for several years just for 1 kilogram of spacecraft. For a 1,000-kilogram vessel, we're now talking about energy demands that equal the output of major power plants running for thousands of years. The numbers have exploded into ranges that dwarf any power generation capability humanity currently possesses. And here's where it becomes truly absurd for Breakthrough Starshot's goal of 20% light speed. Even their gram-scale spacecraft, weighing just a few grams, would require energy equivalent to roughly 100 nuclear reactors, running for several minutes. This is for a payload so small you could hold it in your hand. To push a few grams of spacecraft and sail to 20% light speed requires the continuous output of 100 nuclear power plants. Let me give you a thought experiment that illustrates just how staggering these energy requirements become. Imagine we built a miraculous spacecraft that could maintain constant acceleration at 1g, Earth's gravity. Your crew would experience normal Earth weight the entire journey, which would be comfortable and healthy. With this magic 1G spacecraft, you could reach Mars in just 2 days. Jupiter would be 1 week away, Pluto 3 weeks. After 1 full year of continuous 1G acceleration, you'd be approaching the speed of light itself. Sounds perfect, right? Here's the problem. Maintaining 1G acceleration for 1 full year would require more energy than humanity has produced in its entire history. Every power plant, every gallon of gasoline, every lump of coal ever burned, every nuclear reactor ever operated, add it all up across all of human civilization, and it wouldn't be enough to run this 1G ship for a year. And that calculation assumes a propulsion system with 100% efficiency, meaning every single joule of energy input becomes velocity with no waste. Such a system doesn't exist and probably can't exist. Real rocket engines, even our best ones, are lucky to achieve 1 or 2% efficiency. Most of the energy goes into heat light and other forms that don't contribute to thrust. If we factor in realistic efficiency, the energy requirements multiply by another factor of 50 to 100. We're not talking about engineering challenges anymore. We're talking about energy demands that may exceed what's physically possible to generate and store in a moving vehicle. The energy problem doesn't end with acceleration. Consider what happens over the course of a long journey. The Voyager spacecraft carry radioisotope thermoelectric generators, essentially nuclear batteries. These devices convert the heat from radioactive decay of plutonium-238 into electricity. When Voyager 1 launched in 1977, its RTGs produced about 470 watts of power, enough to run a few light bulbs. After 47 years of operation, those same RTGs now produce only about 220 watts. They've degraded to roughly 47% of their original output. The plutonium continues to decay, generating less heat, and the thermoelectric converters deteriorate over decades in the harsh space environment. By 2025, Voyager will have to shut down most of its remaining instruments because there simply won't be enough power even for basic communication and housekeeping. And this is just 47 years, barely a human lifetime. An interstellar journey to even the nearest star would take thousands of years at our current speeds or decades, even with revolutionary propulsion. How do you maintain power systems for decades or centuries? Solar panels degrade. Nuclear fuel runs out. RTGs lose efficiency. Every power source we know of either depletes or deteriorates over time. The Parker Solar Probe faces this challenge too, though on a shorter timescale. Its solar panels, while operating in the intense radiation near the sun, require complex cooling systems to prevent them from melting. These systems degrade over time. The mission is designed to last about 7 years, because that's roughly how long the spacecraft's systems can maintain functionality in that brutal environment. After 7 years, degradation will have taken its toll. The universe doesn't just make travel slow through distance, it makes maintaining systems over the required timescales nearly impossible. You need energy to accelerate energy, to operate during the journey energy, to communicate home energy, to conduct science at your destination. And every energy source we know of either runs out, degrades, or both. Here's another way to understand the magnitude of the problem. Every percentage point of additional speed costs exponentially more energy. Going from 0 to 1% of light speed might require the energy of 1,000 nuclear bombs. Going from 1% to 2%, you need to add 3,000 more bombs worth of energy. From 2 to 3%, another 5,000 bombs worth. The energy tax increases with each increment. This is why even our most optimistic nuclear propulsion concepts struggle. Project Orion, which would literally ride nuclear explosions, might achieve 3 to 5% of light speed by detonating hundreds or thousands of nuclear devices. But to go faster, to reach 10 or 20%, you'd need exponentially more bombs. At some point, you're carrying so many nuclear devices that their mass alone makes acceleration impossible. Chemical rockets store energy in molecular bonds, breaking and forming chemical bonds between atoms. It's the weakest form of energy storage we use for propulsion. Nuclear fission splits heavy atoms, releasing energy from the strong nuclear force, millions of times more energetic than chemistry. Nuclear fusion combines light atoms, releasing even more energy. Antimatter annihilation, where matter and antimatter completely convert to energy, represents the theoretical maximum, where energy equals mass times the speed of light squared Einstein's famous equation. But even antimatter faces insurmountable practical barriers. We've produced only nanograms of antimatter in all of human history. A nanogram is 1/1000th of a gram. Production costs, if we tried to scale up with current technology, would exceed trillions of dollars per gram. It would take current production methods about 100 million years to produce a single gram of antimatter. And if you somehow had a gram of antimatter storing it without it touching normal matter and annihilating in a nuclear scale explosion, is nearly impossible. A single containment failure means your fuel tank explodes with the force of a large nuclear bomb. Even if we solved production and storage, two enormous ifs, the amount required remains daunting. To accelerate a modest 10-ton spacecraft to 10% of light speed using perfect antimatter propulsion would require roughly 5 tons of antimatter. 5 tons of the most expensive, dangerous, and difficult to produce substance imaginable. We can't produce 5 nanograms efficiently, let alone 5 tons. The energy barrier operates at every level and punishes every ambition. The faster you want to go, the exponentially more energy you need. The longer your journey, the more your power systems degrade. The larger your spacecraft, the more energy required to accelerate it. Every solution creates new energy, demands that spawn new problems. This is the energy barrier. Not a wall we can't see over, but an exponential curve that becomes steeper with every step until it's nearly vertical. We can climb a little way up, achieving the speeds we have now. But the summit, true interstellar velocity, requires energy on scales that challenge even our theoretical understanding of what's possible. The universe has imposed an energy tax on speed, and that tax increases exponentially. We're trying to pay it with the pocket change of chemical reactions when we need the wealth of entire stars. But even if we somehow found unlimited energy and perfect propulsion, we'd immediately face another barrier, just as fundamental: heat. Because at the speeds we'd need for interstellar travel, the universe itself becomes hostile fire. Here's something that surprises most people. When spacecraft re-enter Earth's atmosphere at hypersonic speeds, they don't heat up primarily from friction. The dominant heating mechanism is compression. As the spacecraft plows through air at 28,000 kilometers per hour, it compresses the gas ahead of it, and compressed gas gets hot, extremely hot. The space shuttle's heat shield endured temperatures around 1,650 degrees Celsius during re-entry, hot enough to melt most metals. But the shuttle was traveling at just 0.3% of light speed, and it only experienced this heating for about 15 minutes during atmospheric re-entry. Now imagine traveling at meaningful fractions of light speed through space for years or decades. What happens to your spacecraft? Let's start with the basics. The Parker Solar Probe. Our fastest spacecraft requires extraordinary thermal protection, despite moving at only 692,000 kilometers per hour, just 0.064% of light speed. Its heat shield is made of carbon composite foam, 11.4 centimeters thick, specifically engineered to survive the intense environment near the Sun. At perihelion, closest approach, the Sun-facing side of this shield reaches 1,370 degrees Celsius. That's hot enough to melt many metals, hot enough to make glass run like water. Yet just centimeters behind that shield, the spacecraft's instruments sit comfortably at room temperature around 30 degrees Celsius. This remarkable temperature gradient is what keeps Parker's electronics from frying. But here's the crucial question. Why does Parker get so hot? It's not traveling through any atmosphere. Space near the Sun, like all of space, is an excellent vacuum. So, what's heating the spacecraft? The answer: compression of particles and radiation. Parker isn't experiencing friction in the traditional sense because there isn't enough matter to create continuous friction. Instead, it's being bombarded by the solar wind, a stream of charged particles flowing from the Sun, and by intense electromagnetic radiation. When you're traveling fast and particles hit you, they don't gently bounce off. They impact with tremendous kinetic energy, and that energy converts to heat. This principle becomes devastating at higher speeds. Let's explore what happens as velocity increases. When spacecraft move through space, they're not traveling through perfect vacuum. Interstellar space contains roughly 1 hydrogen atom per cubic centimeter. That sounds incredibly sparse, and it is compared to air, which has about 25 quintillion molecules per cubic centimeter at sea level. Interstellar space is a better vacuum than anything we can create in laboratories. But at high speeds, even that 1 atom per cubic centimeter becomes a significant problem. Here's why the kinetic energy of each collision increases with the square of velocity. At 1% of light speed, that single hydrogen atom per cubic centimeter becomes a problem. The atoms hit your spacecraft with enough energy to create ionizing radiation. The cumulative effect is like flying through a continuous, low-intensity particle beam from a nuclear reactor. No material on Earth can withstand this environment indefinitely. Your hull would be subjected to radiation damage, steady heating, and gradual erosion from the billions of atomic impacts per second per square centimeter. The heating doesn't increase linearly with speed. It increases with the cube of velocity. This cubic relationship comes from two factors. You encounter more particles per second as you go faster, linear with velocity, and each particle hits harder, energy scales with velocity squared. Multiply these together, and you get a cubic relationship. Double your speed, and the heating increases 8-fold. Triple your speed, and heating increases 27-fold. At 10% of light speed, the situation becomes critical. Each hydrogen atom hitting your spacecraft now carries energy comparable to gamma rays, the most penetrating form of electromagnetic radiation. These impacts don't just heat your hull, they ionize atoms throughout the material structure. Electrons are stripped from atoms in your spacecraft's hull. The material itself becomes plasma at the impact points. Your hull isn't just being heated, it's being fundamentally altered at the atomic level, experiencing radiation damage that accumulates with every atom that strikes it. At 20% of light speed, the target velocity for breakthrough starshot, the environment becomes nightmarish. Every hydrogen atom impacts with tremendous energy. A dust grain, even a tiny speck weighing just 1 milligram, carries kinetic energy equivalent to roughly 450 kilograms of TNT, nearly half a ton of explosives. A single dust grain impact wouldn't just damage your spacecraft, it would obliterate it utterly. The explosion would vaporize metal shatter composites and potentially destroy everything within meters of the impact point. Think about what this means. Hitting a speck of dust, something so small you can barely see it with the naked eye, becomes equivalent to being hit by a small bomb. And you can't see these dust grains coming. You can't track them. You can't dodge them. They're simply there, invisible hazards scattered throughout interstellar space, waiting to destroy any fast-moving spacecraft unlucky enough to encounter them. And this continues, not for seconds or minutes, but for years or decades of travel. Breakthrough. Starshot's proposed journey to Proxima Centauri would take 20 years at 20% of light speed. That's 20 years of continuous bombardment by hydrogen atoms carrying gamma ray energies, 20 years of risk from dust grain impacts, 20 years in an environment more hostile than anything humans have ever built machines to survive. The proposed solution for Breakthrough Starshot is telling, make the spacecraft so tiny, just a few grams of electronics and sensors with a meter-scale sail, that the probability of hitting a dangerous dust grain is reduced to acceptable levels. They're not solving the heat and collision problem. They're trying to make the spacecraft so small it can thread between the bullets. But this approach only works for tiny, expendable probes. What about larger spacecraft? What about vessels capable of carrying sophisticated scientific instruments, let alone human crews? The larger your spacecraft, the higher the probability of catastrophic dust grain impacts during any multi-decade journey. Various solutions have been proposed, none entirely satisfactory. One concept involves magnetic shielding, creating a bubble of intense magnetic fields around your spacecraft to deflect charged particles. The magnetic field would bend the paths of protons and electrons, making them curve around your spacecraft instead of hitting it directly. This sounds promising until you examine the details. Creating magnetic fields strong enough to deflect relativistic particles requires superconducting non-magnets of enormous size, consuming tremendous amounts of power. We're talking about magnetic fields that extend hundreds or thousands of kilometers ahead of your spacecraft. The power requirements alone might rival the propulsion energy, and magnetic fields by their nature only affect charged particles. Neutral atoms, like those hydrogen atoms in interstellar space, pass right through magnetic fields unaffected, and dust grains, whether charged or neutral, are too massive to be significantly deflected by any achievable magnetic field. Another proposed solution is ablative shielding, a sacrificial shield positioned ahead of your spacecraft that slowly vaporizes, carrying away heat and absorbing impacts. The shield would be made of material specifically chosen to absorb energy efficiently, gradually boiling away as it protects the spacecraft behind it. But ablative shields have a fundamental problem: they run out. The shield mass must be large enough to survive the entire journey, which could be decades at high speed, and shield mass means more mass to accelerate, which requires more energy, which brings us back to the energy barrier. Every solution to one problem creates or exacerbates another problem. The heat barrier is real and unforgiving. Velocity doesn't just require energy to achieve, it requires surviving the consequences of that velocity. At the speeds we need for interstellar travel, the universe itself becomes a hostile environment of radiation, heat, and kinetic impacts. We're not just traveling fast, we're flying through a continuous bombardment that tests the limits of material science and engineering. This is why even our most optimistic interstellar concepts struggle. The energy to accelerate is one problem. Surviving the journey at those speeds is an entirely separate problem, potentially even harder to solve. The universe has imposed multiple barriers, each one severe, each one potentially insurmountable, with technologies we understand today. So we've seen that energy requirements explode exponentially with speed, and that high velocities create thermal and radiation environments we don't know how to survive. But there's yet another barrier, equally fundamental: control and navigation at these speeds. So far, we've discussed the challenges of achieving speed and surviving the journey. But even if we solved those problems, we'd face another fundamental barrier: navigation. At interstellar distances, hitting your target becomes almost impossibly difficult, and the consequences of small errors are catastrophic. Let's start with a problem. Most people don't consider the stars themselves are moving. When you look up at the night sky, the stars appear fixed in place, eternal and unchanging. But that's an illusion created by the vast distances involved. Every star in our galaxy is in motion, orbiting the galactic center at hundreds of kilometers per second, and each star has its own peculiar motion. Movement relative to its neighbors. Proxima Centauri, our nearest stellar neighbor, is moving at roughly 24 kilometers per second relative to our Sun. That might not sound like much compared to the speeds we've been discussing, but over the timescales required for interstellar travel, at our current speeds, it matters enormously. Consider this: in 1,000 years, Proxima Centauri will have moved about 24 million kilometers from where it is now. That's roughly 60 times the distance from Earth to the Moon. If you launched a spacecraft today, aimed at where Proxima Centauri is right now, and that spacecraft took thousands of years to make the journey, it would arrive at empty space. The star would have moved. This means you can't aim at where the star is. You must aim at where the star will be when your spacecraft arrives. It's like shooting at a target that's running away from you, except the target is 4 light years distant and moving, and your bullet takes tens of thousands of years to arrive. You're not just predicting where the target will be, you're predicting where it will be after traveling for longer than human civilization has existed. But navigation errors compound in another, even more insidious way. Small initial errors accumulate over distance. Let's imagine a spacecraft launched toward Proxima Centauris at Voyager's current speed, which would take about 70,000 years to make the journey. Suppose there's a tiny navigation error at launch, just 0.001 degrees off course. That's an incredibly small error, far smaller than our best navigation systems can achieve. Over the course of 4.2 light years, the distance to Proxima Centauri, that tiny 0.001 degree error translates to missing your target by about 116 billion kilometers. To put that in perspective, the distance from the Sun to Pluto is roughly 6 billion kilometers. Your spacecraft would miss Proxima Centauri by nearly 20 times the width of our entire solar system. One minuscule error in initial trajectory, and your mission ends in empty interstellar space, with the target star just a bright point of light impossibly far away. This accumulation of error is exponential with distance. Double the distance, and your missed distance doubles. Travel to a star twice as far, and that same 0.0001 degree error means you miss by 232 billion kilometers instead of 116 billion. There's no forgiveness for imprecision at interstellar scales. And here's what makes this particularly challenging. You can't easily correct course during the journey. When you send a signal to a spacecraft near Proxima Centauri, that signal travels at the speed of light and takes 4.2 years to arrive. If the spacecraft responds immediately, that response takes another 2 years to reach Earth. One command and response cycle takes 8.4 years. Compare that to Voyager. When we send a command to Voyager 1 currently, about 24 billion kilometers away, the signal takes about 22 hours to arrive. If Voyager responds, we receive that response 22 hours later. A complete command cycle takes less than 2 days. This is challenging but manageable. We can still exercise some control, albeit with significant delays. But 8.4 years, that's not control. That's communication with a historical artifact. By the time you receive a response to your command, nearly a decade has passed. The spacecraft has traveled billions of kilometers from where it was when you sent the command. Any problem that required immediate attention would have resolved itself, one way or another, years before your instructions arrived. New Horizons provides a sobering example of what navigation precision requires. During its flyby of Pluto in July 2015, the spacecraft was traveling at about 50,000 kilometers per hour. To successfully image Pluto and its moons, New Horizons needed to pass within a specific corridor. Mission planners required accuracy within about 100 kilometers. Think about that. After a journey of 5 billion kilometers, lasting 9.5 years, they needed to hit a target window of 100 kilometers. That's like throwing a dart from New York to Los Angeles and hitting a target the size of a city block. The precision required was extraordinary. And because the signal delay to Pluto was 4.5 hours each way, New Horizons couldn't be controlled in real time during the critical flyby. Everything had to be pre-programmed. The spacecraft executed its observation sequence, autonomously taking images and measurements according to instructions uploaded weeks earlier. By the time mission controllers saw the data coming down, the flyby was already over. It worked. New Horizons threaded the needle perfectly, delivering stunning images of Pluto's surface. But this was within our solar system, where we could track the spacecraft precisely where course corrections were possible during the long cruise phase, where the target wasn't moving relative to the sun. For an interstellar mission, the challenges multiply by factors of millions. There's another subtle but important issue: relativistic effects on timekeeping. Even the GPS satellites orbiting Earth, moving at a relatively sedate 14,000 kilometers per hour at an altitude of 20,000 kilometers, experience time dilation. Their clocks run slightly differently than clocks on Earth's surface, about 38 microseconds per day, differently when you account for both the velocity effect and the gravitational effect. 38 microseconds might not sound like much, but if GPS didn't correct for this, the system would accumulate errors of about 10 kilometers per day. Your GPS would be useless within hours if relativistic effects weren't carefully accounted for. Now, imagine a spacecraft traveling at 10% of light speed. At that velocity, time dilation becomes about 0.5%. The spacecraft's clock runs measurably slower than clocks on Earth. Over years of travel, this accumulates. Navigation calculations, trajectory, predictions, and course corrections all become significantly more complex when you must account for the fact that time itself is passing at different rates for the spacecraft and mission control. The navigation problem has no easy solution. You can't see interstellar hazards coming. Dust grains that could destroy your spacecraft are invisible until impact. You can't control the spacecraft in real time across light years of distance. You can't correct small errors that accumulate into huge missed distances. You must predict where a moving target will be thousands of years in the future and thread a needle across distances measured in trillions of kilometers. When we talk about interstellar travel, we often focus on propulsion, how to go fast enough. But navigation may be equally difficult. You must not only go fast, but arrive at the right place at the right time with navigation precision that exceeds anything we've ever achieved, maintained over timescales longer than human civilization, with no ability to correct errors for years or decades after they occur. This is the navigation barrier. It's not as dramatic as the energy barrier or the heat barrier, but it's just as fundamental and potentially just as insurmountable with current technology. And even if we could navigate perfectly across light years, one final challenge remains: staying in touch with home. Because at interstellar distances, even communication, sending and receiving simple radio signals, becomes nearly impossible. Let's talk about something that might seem straightforward: sending a radio signal across space. You point an antenna, you transmit, and someone on the other end receives your message. Simple, right? But at interstellar distances, even this basic task becomes almost impossibly difficult. And if you can't communicate with your spacecraft, you can't receive its data, making the entire mission nearly pointless. New Horizons teaches us a valuable lesson about the challenges of deep space communication. During its 9-day flyby of Pluto in July 2015, the spacecraft collected about 50 gigabits of data, images, measurements, spectrometer readings, everything it could gather during its brief encounter with this distant world. The spacecraft was 5 billion kilometers from Earth. Light speed signals took 4.5 hours to travel each way. Now, here's the sobering part. Transmitting all that data back to Earth took 16 months. 16 months to send 50 gigabits of information. The spacecraft's transmitter operated at just 12 watts of power, about the same as a small household light bulb, and could send data at only 1 to 2 kilobits per second when transmitting to Earth from Pluto's distance. Think about that data rate. Modern home internet operates at millions of bits per second. Your smartphone downloads faster than New Horizons could transmit from Pluto, and receiving those faint signals required enormous 70-meter dish antennas on Earth, precisely pointed at New Horizons' location, listening intently for the whisper of that 12-watt transmitter across 5 billion kilometers. Why so slow? The answer lies in one of the most fundamental laws of physics, the inverse square law. Signal strength decreases with the square of distance. Double the distance, and your signal becomes 4 times weaker. Increase distance by a factor of 10, and the signal weakens by a factor of 100. The relationship is brutal and unforgiving. Pluto is far, but Proxima Centauri is roughly 8,000 times farther, 40 trillion kilometers versus 5 billion kilometers. If signal strength decreases with distance squared, then at Proxima's distance, the signal from a 12-watt transmitter like New Horizons would be about 64 million times weaker than it was at Pluto. Let me spell out what this means. With the same 12-watt transmitter that New Horizons uses, transmission from Proxima Centauri would occur at roughly 0.015 bits per second. Not kilobits, bits. It would take weeks to transmit a single low-resolution image. A high-definition photograph might take years, a few minutes of video decades or centuries to transmit. And remember, this is assuming you could even detect the signal at all. At those power levels and distances, the signal would be almost indistinguishable from cosmic background noise. You'd need receiving antennas far larger than anything we've ever built. So what are the solutions? The obvious one is to increase transmitter power. If you need the signal to be stronger, use more power. But power requires energy, and energy requires mass, either in the form of fuel or power generation equipment. A spacecraft operating at megawatt power levels would need a substantial nuclear reactor, adding hundreds or thousands of kilograms of mass. And we're back to the energy barrier. More mass requires more energy to accelerate. For breakthrough, Starshot's proposed gram-scale spacecraft, meaningful communication is nearly impossible. The entire spacecraft weighs a few grams. There's no room for a powerful transmitter, no mass budget for a large antenna, no space for substantial power generation. The spacecraft could make measurements, but sending that data back to Earth across 4.2 light years with gram-scale power and antenna size might be impossible. The alternative is to make the receiving antenna larger. A larger antenna can collect more of the faint signal, like a bigger bucket catching more raindrops. But the antennas required for interstellar communication aren't measured in meters, they're measured in kilometers. To reliably receive signals from a modest power transmitter at Proxima Centauri, you'd need a receiving antenna on Earth with a diameter of several kilometers. Nothing even remotely approaching that scale exists today. Voyager provides our current practical limit for deep space communication. At 24 billion kilometers, about 163 astronomical units, Voyager 1's 23-watt transmitter produces a signal that reaches Earth with a strength of about 1/10 million billionth of a watt. That's a decimal point followed by 15 zeros before you get to a number. To detect this whisper, NASA uses 70-meter dish antennas with incredibly sensitive receivers. And even then, Voyager can only transmit at about 160 bits per second, and Voyager's signal continues to weaken as it moves farther from Earth. The inverse square law continues its relentless work. By the early 2030s, Voyager's signals will likely become too weak to detect reliably even with our best antennas. The spacecraft will still be operating. It will still have enough power from its degrading RTGs to run basic systems, but will no longer be able to hear it. It will fall silent, not because it failed, but because distance has finally defeated communication. From Proxima Centauri, 8,000 times farther than Pluto, the challenges are qualitatively different. You'd need either transmitter power in the megawatt range, requiring massive nuclear reactors, or receiving antennas on Earth with collecting areas measured in square kilometers. Neither is feasible with current or near-term technology. There's another factor that makes interstellar communication even harder. You need to point your antenna precisely. At interstellar distances, the beam from even a large antenna spreads out enormously. If your spacecraft's antenna isn't pointed correctly, if it's off by even a fraction of a degree, the signal misses Earth entirely, spreading out into empty space where no one will ever receive it. Keeping an antenna pointed at Earth while traveling at high speed, while your spacecraft potentially tumbles or rotates, while dealing with navigation uncertainties for decades of travel, that's an extraordinary technical challenge in itself. New Horizons had to execute careful maneuvers to keep its antenna Earth-pointed during the Pluto flyby. For an interstellar spacecraft, you'd need to maintain that pointing for not hours, but years or decades. Here's what all this means. Interstellar exploration isn't just about getting there. It's about staying in contact, sending back the precious data you collect, letting the humans who built and launched know what you've discovered. And with our current understanding of physics and engineering, communication from the nearest stars is nearly as difficult as the journey itself. You could send a spacecraft to Proxima Centauri, and it might successfully arrive, make observations, and collect data. But if it can't send that data back, if it can't communicate what it found, then in some sense the mission has failed. The spacecraft becomes like an explorer who travels to a distant land but never returns to share what was learned. The journey happened, but the knowledge remained locked away, unreachable. This is the communication barrier, not as dramatic as the energy or heat barriers, but equally fundamental. We're not just slow at traveling through space. We're also nearly deaf and mute across the vast interstellar distances. The silence of space isn't poetic metaphor, it's practical reality. So, here we are, having examined every barrier propulsion energy, heat navigation, and communication. It's time to take stock of where we actually stand, not where we hope to be, not where science fiction imagines, but where we truly are right now. After exploring every aspect of interstellar travel, propulsion energy, heat, navigation, and communication, we can finally answer the question we started with: how fast can we actually travel in space right now? The answer, stated simply, our fastest spacecraft ever, the Parker Solar Probe, reaches a peak velocity of 692,000 kilometers per hour. For typical interplanetary missions, speeds range from 40,000 to 100,000 kilometers per hour. The fastest humans have ever traveled remains 39,897 kilometers per hour, achieved by the Apollo 10 crew in 1969, a record that stands unbroken after more than half a century. These speeds are adequate for exploring our solar system, though missions require years or decades. To the moon, we need 3 days with Apollo-era technology. To Mars, 7 to 9 months is typical. Jupiter requires 5 to 6 years, even with gravity assists. Saturn demands 7 years. Pluto took New Horizons 9.5 years to reach, and reaching the edge of our solar system Voyager has been traveling for 35 years and is only now entering interstellar space. But to Proxima Centauri, our nearest stellar neighbor, at our current speeds, 70,000 to 115,000 years. Not decades, not centuries, tens of thousands of years, timescales that dwarf all of recorded human history. We've now identified 5 fundamental barriers that make interstellar travel so devastatingly difficult. First, the rocket equation. Every bit of additional speed requires exponentially more fuel. Chemical rockets have already achieved 98% of their theoretical maximum exhaust velocity. There's no breakthrough coming in chemical propulsion. We've hit the ceiling imposed by the laws of chemistry itself. Second, the energy barrier. Kinetic energy increases with the square of velocity. To accelerate just 1 kilogram to 1% of light speed requires the energy of a nuclear bomb. To reach 10% of light speed requires energy equivalent to major power plants running for years. The energy demands scale exponentially, quickly exceeding anything we can practically generate or store. Third, the heat barrier. At high speeds, collisions with interstellar hydrogen atoms create heating comparable to nuclear reactor radiation at 1% of light speed and become devastating at 10 or 20%. No material we currently know of can survive sustained travel at these velocities. The universe itself becomes a hostile environment of heat and radiation. Fourth, the navigation barrier. Small initial errors accumulate over interstellar distances into enormous misdistances. A 0.01 degree error becomes a 116 billion kilometer miss at Proxima Centauri. Stars themselves are moving targets, requiring predictions of their positions thousands of years in the future. Real-time control is impossible when signals take 8.4 years for a round-trip communication. Fifth, the communication barrier. Signal strength decreases with the square of distance. From Proxima Centauri, even a 12-watt transmitter would send data at a glacial 0.05 bits per second. Meaningful communication requires either enormous transmitter power or kilometer-scale receiving antennas. Neither is currently feasible. These aren't engineering problems that clever design can solve. They're fundamental physical constraints imposed by the structure of our universe. Now, what about near-term improvements? Technologies currently under development might offer incremental gains. Nuclear thermal rockets, which NASA is actively testing, could achieve speeds of 100,000 to 150,000 kilometers per hour. This would cut Mars transit from 9 months to 3 or 4 months, revolutionary for solar system exploration. Nuclear electric propulsion combined with ion drives might reach 200,000 kilometers per hour. Vesimir, if it succeeds, might achieve similar speeds and potentially cut Mars transit to 39 days. These improvements matter enormously for exploring our cosmic neighborhood. A nuclear thermal rocket makes Mars missions practical and safe for humans. Nuclear electric enables missions to the outer planets that would be impossible with chemical rockets alone. But even with these advances, Proxima Centauri still requires more than 10,000 years. We've improved by a factor of perhaps 5 or 10. We need to improve by a factor of 10,000. What about more speculative technologies? Fusion rockets, if we can master fusion power, might achieve 3 to 5% of light speed. Nuclear pulse propulsion, Project Orion, could theoretically reach similar velocities, but faces insurmountable political barriers. Laser sails, like Breakthrough Starshot, aim for 10 to 20% of light speed, but require infrastructure exceeding anything humanity has ever built. Antimatter propulsion offers theoretical maximum efficiency, but faces production and storage challenges that may remain unsolvable for centuries. All of these technologies require decades or centuries of development. None are right now. None are even soon. They're distant possibilities, not practical solutions for current interstellar exploration. So here's our honest reckoning. The solar system is within our reach. We can send robotic probes to every planet, though missions take years. We've mastered our immediate neighborhood. Every planet has been visited. We have orbiters, landers, and rovers at multiple destinations. We've sent spacecraft into interstellar space. This is genuine achievement representing humanity's first steps beyond our birth world. But interstellar travel remains completely beyond our current capabilities. We would need breakthrough physics or revolutionary technologies we haven't yet conceived. There is no solution just around the corner. The challenges aren't primarily engineering, they're fundamental physics. The distances are so vast and our speeds so limited that the nearest stars might as well be in another universe. We can improve our technology. Nuclear propulsion will make solar system exploration faster and safer. Better ion drives will enable missions currently impossible. Advanced materials might allow us to survive harsher environments. But none of these improvements, even combined, bridge the gulf to practical interstellar travel. The universe has imposed multiple barriers, each one severe, each one potentially insurmountable. With technologies we understand today, we're not slightly too slow, we're orders of magnitude too slow. We're not almost there, we're barely begun. This isn't pessimism, it's honest assessment. We've achieved extraordinary things in just 67 years of spaceflight. We've gone from Sputnik to rovers on Mars, from suborbital hops to landing on comets. We've demonstrated remarkable ingenuity and capability. But the challenges ahead aren't just harder than what we've accomplished, they are qualitatively different, demanding solutions we don't possess and perhaps cannot conceive with current knowledge. The stars remain distant, and we remain slow, desperately, overwhelmingly, almost incomprehensibly slow. But we're learning, adapting, and pushing forward. We're building the knowledge foundation that future generations will use to go farther and perhaps eventually faster. We're not just exploring space. We're learning what exploration requires, mapping the boundaries of the possible, understanding what physics allows and forbids. This is where we stand masters of our solar system, but still bound to it by chains of physics and engineering. The stars are within our sight, but beyond our grasp. And whether they'll ever be within reach depends not on engineering improvements, but on breakthroughs we cannot yet imagine.